There we go. Okay, I'll take the silence from the Zoom members as an emphatic yes, that it worked great. So let's go ahead and get started on this first problem. I am kind of cheating a little bit and telling you that this is a good example of an R theta coordinate system problem. So remember in homeworks and on the exams, you're going to be expected to be able to choose which coordinate system is most convenient. And so my clues here, if you weren't to be told ahead of time, my clues that R theta would work well are things like I'm given R as a function of theta, and I'm given this piece of information might actually be confusing because when we're given speeds and time rate of change of speeds usually is like nt coordinate system. And then let's see, but it's asking us a lot about thetas. It's saying when your theta is equal to 1, and we have R in terms of theta. And in fact, they've even already drawn for us the origin, the radial direction, and the direction of positive theta. Okay, so those are all pretty big clues that that's a good coordinate system. All right, I'll leave it there and go ahead and let you get started. So P, the particle, moves along this interesting spiral path where theta is in radians. If it maintains a constant speed of v equals 20 feet per second, determine basically the vector v in terms of r theta coordinates as a function of theta and evaluate each at theta equals to 1. Good morning. It's Catherine Jolie, right? Yes. Great. We're just working on this first problem. I'm gonna give maybe 1 or 2 more minutes, and then I'll start making progress on the board. Okay. All right. So what I already wrote is I did kind of just those very first couple of steps where, assuming we chose our theta coordinates as a good set of coordinates for this problem, we're being asked about velocity. So I went ahead and grabbed from your equation sheet the expression for velocity in terms of our theta coordinates, just that general expression. And as soon as we write that down, the next thought in our head should be, okay, I need to go look for each of those variables individually. So that means that we need to go on a hunt for r dot, for r, and then theta dot. So I usually tend to like to work left to right. So my first thought would have been, all right, let's try to find r dot. So find r dot. We are given in the problem that r as a function of theta is equal to 10 over theta feet. So I know I can't take a time derivative of that expression immediately because it's not in terms of time, it's in terms of theta. So my next thought is, aha, we got to do chain rule. So I know that r dot is equal to dr dt, which is equal to dr d theta times d theta dt. And I absolutely can take the derivative of this r expression with respect to theta. So we can find this term. But in this problem, are we given, sorry, let me zoom out here. There we go. Are we given an expression for theta in terms of time that we can take a derivative of? No. So for right now, I'm actually just going to leave this as theta dot. Okay, so let's write out this expression. We'll say dr d theta is equal to what? Well, I can rearrange this a little bit. I can say this is really 10 times theta to the negative 1. In my mind, that makes the derivative easier. So I should have minus 10 theta to the minus 2 is the derivative, times theta dot, or minus 10 over theta squared times theta dot. Okay. That's really all I can do with r dot at this point. That's as far as I can get. So my next thought is, maybe your next thought is look at r. You could look at r. That's the next variable in our sequence here. Well, I know from the problem that r is just 10 over theta, and I could go ahead and plug in theta equals to 1 radians if I were interested in what is r when theta equals 1. Well, that's 10 over 1 is 10. Okay, that's as far as I can get there. Theta dot. This is where things get interesting. My next thought is let's try to scour this problem for any extra information we've been given to see if there's any chance we can get a theta dot from there. So we know it's not a traditional problem where I'm given theta as a function of time, so I can't take a time derivative of some expression to find theta dot. So what do I do? Is there any information we haven't used yet? Beautiful. We have not used this information that the speed is constant at 20 feet per second, okay? So my next question is, how can I use this info that says constant speed of v equals 20 feet per second? Any ideas?
So your magnitude of your velocity equation that you have are if you keep theta and theta dot and you just plug in and then set it equal to what is it? It's the u theta component squared plus the u bar component squared all square rooted.
Beautiful. Absolutely. So a couple of steps got covered there. First is I realized that I can make use of this very first equation here for velocity, and I can plug in what I already know about r and r dot. I can take a magnitude of that expression and set it equal to 20. That's what this piece of information tells me. Okay, so if I want to write velocity equals to r dot, well, I'm going to go ahead and plug in this expression that we found for r dot. So that would be minus 10 over theta squared times theta dot, all times u hat r, plus r times theta dot. So that's going to be, we have for r is 10 over theta, and then times theta dot in the u hat theta direction. Okay, now I need to take a magnitude. So the magnitude of the velocity equals the square root of each component squared. So minus 10 over theta squared times theta squared plus 10 over theta, theta dot squared. And all of that given to us in the problem is 20 feet per second. Now what?
Solve for theta dot.
Beautiful, absolutely. Solve for theta
Or
dot.
plug
We're
in
on.
one. Yeah, and then do that.
Yep, we're on a hunt for theta dot. We have an expression for theta dot. It's kind of gross right now, but we can manipulate it and solve for theta dot. So that's what I'll do. And I'll be quite honest, this gets a little bit gross. So this ends up being minus 10 over theta squared times. Did I do that right? No, I didn't. This is
This.
theta dot.
I thought it was just r dot for
Wait a minute.
VR.
Yeah, what is our...
R
Sorry,
dot is
that one.
negative 10 over theta squared.
Times theta dot. Right, because it's right here. Do you agree with this now, Samuel?
I don't know why you're multiplying by theta dot.
So r dot up here
Uh-huh.
is equal to dr d theta times d theta dt. So we found this is the expression for r dot. I'm circling it right now.
That makes sense.
Okay, okay, good. Okay, I think I fixed it. Y'all agree? Okay, good, okay. Let's see. Theta dot squared plus 10 over theta times theta dot all squared equals 20 squared. All right, we're gonna have to square these terms. So I've got 100 over theta to the fourth times theta dot squared plus 100 over theta squared times theta dot squared equals 20 squared. Okay, I'm seeing a common term here on the left, so I'm going to factor out my theta dot squared. This will be theta dot squared times 100 over theta to the fourth plus 100 over theta squared equals 20 squared. Now I can bring this term over to the right-hand side. Okay, looks like I just need to take a square root and then I'll have an expression for theta dot. But I'm actually going to simplify a little bit more before I do that. I'm going to take out a common term in this denominator. It looks like I have a 100 in common, but I also have a theta to the fourth on the bottom in common if you squint your eyes just right. So 20 squared. Let's see if you agree with this. 1 plus theta squared. Yeah? So if I divide this term by theta to the fourth, I'll get a theta squared on the bottom.
Dr. Higgins,
Yes.
at this point, could we also substitute in theta equals 1?
I like to wait until the end,
Hmm.
Especially because it's asking me for two things. It's asking me for VR and V theta as functions of theta. And then separately, it's asking me to plug in theta equals to 1. So I haven't gotten far enough to answer this first part of the problem yet.
Okay. Thank you.
Yeah, great question. Okay, and now I can take my square root. Theta dot equals, well, the squared just goes away on the 20. The square root of 100 over theta to the fourth should be 10 over theta squared times square root of 1 plus theta squared. And if I take this bottom term, flip it and multiply it, we should be able to reduce this even further. I should just get 2 theta squared over square root of 1 plus theta squared. We okay with that? Now what? Am I done? Plug it back in. So we got to plug it back into our velocity expression. So velocity is r dot u hat r. R dot was this thing, minus 10 over theta squared times theta dot. It's 10 over theta squared times theta dot u hat r plus r theta dot. So r was 10 over theta. 10 over theta times theta dot, which we now know is 2 theta squared over the square root of 1 plus theta squared. All of this is our u hat theta. And that is the answer to the first part. Oh, you know what? I can fill in one more thing. There's one more substitution I didn't do. What am I missing? Yep, my theta dot in the radial part of the expression. Let's go ahead and fill that in. I just need a little extra room. I have an expression for theta dot, which is 2 theta squared over square root 1 plus theta squared. All right, little nasty. Not so pretty, but we did it. Last part is they want us to plug in for theta equal to 1. So V of theta equals to 1. That's super simple. We just plug in 1 for all of our thetas. So if you want to check yourself, your algebra should come down to minus 20 over square root of 1 plus 1. You have r plus 20 over square root 1 plus 1. You have theta, which comes down to minus 14.1. You have r plus 14.1. You have theta. Alrighty. Any questions on this one? Now, I believe, is this the one that I marked out? No, okay, all right. So I'm looking at this, I'm thinking, well, thank goodness they didn't ask me for acceleration because that's gonna take even more derivatives, right? We probably could have done it, but it would get long and gross. And in fact, on this next problem, the original problem does ask for acceleration, but the derivatives just get really onerous. So for today, I am just asking you to find velocity for this problem. Okay, so moving on to our next topic, dependent motion. We have 2 particles that are connected by an inextensible cord. Notice that the problem statement doesn't tell you that it's inextensible, but in this class, it's okay to assume that. Just understand that that is an assumption that you are making. So let's talk about being practical engineers for a second. Let's say you arrive at your company and your system has some sort of rope, like an actual rope that is connecting 2 pieces, and you're trying to do the kinematics analysis of these 2 things that are moving. If you make the assumption that your rope is inextensible, what is the possibility for error there? What?
The rips or the stretches or anything slightly off.
Yeah. So let's think about where that assumption might be really good. So let's say your rope is like a 1/4 inch in diameter and you're lifting it, maybe it's like paracord rope, and you're lifting 2 items that weigh like 200, 300 pounds each. What's the likelihood that that rope is going to stretch by a significant amount? I'm thinking it's pretty good. Like if you practically play around with some paracord, you put 200, 300 pounds on each side, it's probably going to change by maybe even on the order of inches. Okay. So that means that that assumption is no good anymore. That assumption that it's inextensible is no good. Now, perhaps your paracord stretches initially, but then it settles at a pretty constant length. Okay, maybe your assumption is okay. Now let's think about a steel cable holding to 200, 300 pounds on either side. Do you think that one's going to extend significantly? Probably not. So maybe an inextensible cord assumption is okay. Okay. Question? No? Okay. All right. So roller A is moving up with a velocity of VA equals 3 feet per second and has an acceleration of A equals 4 feet per second squared when SA is equal to 4 feet. Determine the velocity of block B at this instant. Let's work through writing down my given and my find. What am I given? What should I write down here? Okay. Hold on. Let's look even closer at that very first piece of information. So it says VA. Notice it doesn't have a vector arrow and it's not bold, and it gives it to me as just a scalar. So is this the velocity vector of A, or is it giving me the speed of A? In the problem statement, they're giving me the speed of A, but based on the picture, I can interpret the full vector because I know that this particle A can only be going up or down. It has no left and right component at all. It can only go up or down. And in fact, the problem tells me it's moving up. So I can write the speed of A is 3 feet per second, or I could also write that the vector velocity of A equals 3. If I give myself a coordinate system here, and I think the most obvious one is this one. This is 3 I hat or j hat. J hat. Beautiful. You see how I don't just write down exactly what's given. I also try to like massage as much information out of that little piece of information and the picture. That's going to be really important. Okay, what else? What's the next piece?
Acceleration of v squared 40%.
Beautiful. So again, they say acceleration, but it's not the acceleration vector because they've only given me a scalar quantity. So really they're telling me the magnitude of my acceleration vector. Okay, so I'll write it down like the magnitude of A equals 4 feet per second, specifically at the moment when SA equals 4 feet. All right, and then what am I being asked to find? How do I write that in math?
B of B.
Yes, with a vector or not with a vector?
With a vector.
With a vector, yes. They're asking you for the vector velocity of B, specifically at this instant when SA is equal to 4. Okay, what is your very next thought for what to do next when you see this problem with two particles connected by a rope?
Length of rope.
I would write an expression for the length of the rope. All right. In class, I mostly kind of held your hand through all of the examples for finding that expression. I'm going to let you go on your own for now. Give it a shot, and we'll come back together in a few minutes.
Which go down on the
Yep, I'm sorry. It somehow got zoomed again.
I'm stuck on simplifying my length equation.
Okay. Anyone else stuck on simplifying the length expression? Perhaps. Okay, if you're not stuck, just keep working. Samuel, I'll go ahead and put up, I'll get to that point, okay?
Okay.
So, what I'm seeing of this rope is I'm seeing one section that's gonna change in distance and another section that's gonna change in distance. And I need to label those with some variables so I can work with those variables. So I'm gonna say this here can change, and they've unfortunately already used the variable SA, so we'll call this SD. And then there's also this distance between block B and the edge of the pulley. And of course, there's some constant amount of rope that wraps around the pulley. We're not going to worry too much about that piece. Okay, so the length of the rope I have is equal to SB plus SD plus some constant amount. However, we really don't want this SD variable. And in fact, we can write it in terms of the variables that are involved in the problem statement. So we can write an expression for SD that involves SA and maybe another quantity. What do you think is one way to do that?
Um,
Go ahead, Samuel.
I did the square roots, or I used SD is equal to square root of SA squared plus 9 plus 3 squared.
Beautiful. Pythagorean theorem. It's just the distance between those 2 points. We're given 3 as the horizontal distance, SA is the vertical distance. Okay, so I'm going to plug that in, and I'll rewrite L rope is equal to SB plus, I'm actually going to write this as, I'm going to write it this way. We okay with that?
Yeah, that makes sense. I guess we'll just use chain rule. I just didn't want to.
Yes, very unfortunately, we're going to have to like massively chain rule in this problem. So not just once, but we're going to have to do kind of a nested chain rule that gets a little bit gross. But it's okay, we can do it. I promise we can do it. All right, so our next step is, of course, to take the time derivative of all this, which means that L dot is equal to 0.
Excuse me.
Yes.
Since it's a 3-4-5 triangle, can't you just write it as like the 4/5 SA or no?
Yeah, so what's coming up a lot is the question of when do you plug in a specific value versus when do you leave it as a variable? For this problem in particular, it is asking us exactly about this one instant in time where SA is equal to 4. However, is it true that SA is changing over time? Is SA always 4, or does that distance change over time as these things move around? That's a question for you.
Oh, my bad. Changing.
It absolutely is changing, right? So if I were to plug in here, SA equals to 4, and then I try to take a time derivative of that, I'm going to say, oh, the time derivative of 4 is 0. But that's not true because SA changes in time. SA is a function of time. So when we take a time derivative, we have to account for the fact that it can change over time. So we do not want to plug that in instantly. We want to leave SA as a variable because we have to account for the fact that it can change over time.
All right, cool. Thank you.
Does that make sense?
Yeah, no, that makes sense.
Okay, very good. Okay, so this derivative is where things get a little icky. So not icky for SB. That just becomes basically the velocity of particle B. But gets gross for this other part. d dt of SA squared plus 3 squared. All right, so this is where we have that nested chain rule. So we'll have to be careful. The outermost function that I see is this 1/2 SA squared plus 3 squared to the minus 1/2. That's the derivative of the outermost function. Then I need to take the derivative of the inside and multiply that. So the inside I see is 2 SA, but SA in and of itself is also dependent on time. So I actually have to take the time derivative of SA and multiply that as well. I'm not sure if your calculus teacher was as kooky as mine, but mine used to describe problems like this as like a peanut M&M. You had to derive the outer shell first, and then you had to derive the chocolate next, and then you had to derive the peanut in the middle. She was a fun person. Okay. I believe that's it. And this is all equal to 0. Okay. Now I have this nice expression basically for the velocity of B if I'm given some information about the velocity of particle A. Which am I? Yes, of course I am. We got that from the problem statement. There is a little bit of simplification that could be done here, like this 2 and this 1/2 cancel. So I can write dsB dt is equal to minus SA squared plus 3 squared to the minus 1/2 times SA times SA dot. And now I can finally plug in what's happening at this one instant in time. So I'm given that at this one instant in time, SA is 4 feet. Am I given the velocity of A at this instant in time? Yep. It's 3 feet per second. This SA is also going to be 4. So I should get this is minus 4 plus 9 to the minus 1/2 times 4 times 3. And if we simplify that, we get SB dt equals 2.
It's 4 squared, right?
Yes, I apologize. Sorry, I plugged in 3. Why did I plug in 3? No, the 3 was right. It's this that needs to be squared. Yep, got it. Maybe. So we should get 2.4 feet per second. And then to determine the direction, I always like to do this visually. I let my rope expression tell me the amplitude of the motion of the other particle, but visually is how I tell the direction. So if A is going up, we know for certain, very simply, that B must be going to the right. Okay, so my final answer should be this is in the positive I hat direction. If A goes up, B must go to the right. How we feeling now? How was that one? Yep, Thomas?
Can you explain the, like, getting the equation for the road? Like,
Yeah, absolutely.
I don't understand the C.
So, oh, the C? Okay, yeah. So the C is just this blue part. It's just the constant amount of rope that stays in contact with the pulley. So basically, I'm just saying that between that this datum here that describes the right-hand side of SB and this datum here that describes the left-hand side of SD, those never move further or closer to each other. There's always a constant distance of rope between them. So this C is just the constant amount of rope that no matter what happens to SB, no matter what happens to SD, which are growing and shrinking over time, no matter what happens to those, there's a small amount of rope on that pulley that never changes.
And that'll be like for any pulley that you have, you'd have.
Yeah. Yep. So I just say that this is some constant amount of distance of the rope. And when I take the derivative of it, it goes to 0 because it's constant. It's never changing in length. Does that make sense? Okay, very good. Great question.
So we're not doing acceleration for this one.
Nope. Because it got really gross and I don't want to do it. We don't have time.
Where
Yeah.
did the time derivative essay come back in? It's like smack dab in the middle,
This one
the last year. Yes,
or this one?
same. So why does that come back if we solve for the?
I solve for SB dt.
Oh, because SA is a function, you have to do the derivative of that.
Yes. So this is the chain rule. And this is because I'm taking a derivative of this function with respect to time, not with respect to SA. So SA is not the variable in the denominator of that derivative. So I have to go one step further and recognize that SA in and of itself is a function of time. So I have to do that final derivative of my peanut M&M in the middle and say dSA dt at the end. Okay, I'm gonna just clean up my notes a little bit for when I upload them. All right, last problem. Two boats leave the pier at the same time and travel in the direction shown. If VA, which is the speed of boat A, is 40 feet per second and the speed of boat B is 30 feet per second, determine the magnitude of the velocity of boat A relative to boat B. How long after leaving the pier will the boats be 1,500 feet apart? So a two-parter. And I am curious how you do this one completely without assistance. So I'll give you until 10:50. At 10:50, I'll start the problem and hopefully we can finish up by 10:55.
I'm sorry, I got a call. What was your final answer for the last problem?
Yep.
Thank you.
You're very welcome. Thank you.
assuming they both start at 0, 0.
Yep. You can assume they both start at 0, 0. You got it, Micah? You got it?
Yeah.
Very good.
Oh, nothing attached.
Oh, okay.
Oh, no, sorry, no.
Okay, 1050. Walk me through what equation did you write down first?
I'll put mine in Cartesian. I did give A and B.
Okay, so we're being asked about a relative velocity.
Right.
And specifically, what relative velocity are we being asked for? Can you tell me exactly how to write that variable?
B is variable.
We're being asked to find v, the velocity of A relative to B. So A over B. Very good. Okay, so that's what I'm being asked to find. And so now I need to interpret, okay, what equation do I need to use? And we know we have to be careful with this one. What variable goes all the way to the left of the equal sign? VA, yes. So the letter that's on the top of this fraction is also the letter on the left of the equal sign. That's my trick. Equals the other velocity plus the relative velocity. So we need to use this equation, but before I can solve for this, I must be able to plug in VA and VB. So this means that I first need to find VA and VB as vectors. Now, Micah made a really great choice. He decided to use Cartesian coordinate systems. I think that's a great idea. In fact, it's already drawn for you that way. I've already told you an X direction and a Y direction. So let's go write out our expression for VA. I like to draw my Cartesian coordinate system, draw in my vector VA, which has a magnitude of 40 and is 30 degrees from the vertical. So here, I'm going to go a little bit faster on my trig than I have been in problems past. So I have some amount of this vector that goes to the right, some amount that goes up. So the amount that goes to the right is going to be 40 sine 30 I hat. The amount that goes up is 40 cosine 30 j hat. Beautiful. Let's find VB. Draw a similar picture. X, Y. This has a magnitude of 30, 45 degrees from the horizontal. Some component that goes to the right, some component that goes up. VB equals 30 cosine 45 I hat plus 30 sine 45 j hat. Now I can plug these into my relative velocity equation. Solve for my relative motion. I need VA on the left-hand side. Equals VB on the right-hand side. Plus the relative velocity. Now I can solve for V A slash B. Should get, I'm gonna let you do the simplification. I'll give you the final values though. Minus 1.213 I hat plus 13.43 J hat feet per second. But is that what the problem asked me for? Does it ask me for the vector? No, it wants the magnitude of the velocity. So I then need to take the magnitude of this. So the magnitude of VA slash B, the square root of each component squared. Should get 13.48 feet per second. Okay, that's the first part of the problem. Any ideas on the second part of the problem? Okay. How long until boats are 1,500 feet apart? We can assume, because it hasn't told us otherwise, that these velocities are constant. Okay, so the integration actually is much simpler than an integration. It's just that for a constant velocity, or a constant relative velocity, the distance between them at the end minus the distance between them initially over delta t. Only because the velocities are constant. If they weren't constant, we'd have to do a full integration. So what was the initial distance apart? 0, because they both started at the origin. And the final distance is what? We're being asked about 1,500 feet apart. And the constant velocity is 13.48 feet per second. Relative velocity. So delta t comes out to, any ideas, Micah? Beautiful. 111.27 or 28 seconds. And if you're fancy and want to simplify to minutes, it's 1.85. Are you here for the next class or for? Oh. Are we doing that here? We're in 211.
Oh, are you? I thought it
The
was-
the undergrad meeting is 211.
Got it.
Yep.
What undergrad meeting?
All the undergrads that are associated with my research lab. Yes. So everyone doing research with me that is not a graduate student meets together weekly.
How do you do that? If I were to want to do that? Is it too late?
I would actually recommend that you join a different meeting. So the way I try to do involvement in my lab is that I like to meet everyone involved twice a week. Once as a full lab, everyone associated with my lab meets at the full lab group meeting. And then separately for anyone who's active on a research project, meets me some other time during the week. And sometimes it's a team meeting, sometimes it's an individual meeting. It just depends. So with the undergraduate check-in, that's kind of like their second meeting with me. But the full lab group meeting has an open door policy. So anyone who wants to join my really big, large lab group meeting, it happens in this same room, Wednesdays, 4 to 5 p.m. And you're welcome to join those.
Okay, what would that involve? Like with that?
You just come in the room and sit down and find out about what projects are going on in my lab. So sometimes what happens is I'll have a side item that comes up that really needs to be done, but everyone else is kind of focused on their own project. And that's when I kind of ask the room at large, if there's anyone that's not currently active on a project that can do this thing for me, it's all yours. And then it morphs into being an active project usually. Does that make sense?
So how many projects would you say you have going at like a given month under your lab?
Too many.
So one of the kids I was in classes, he was working on, because I was looking at some of your like your unicycle stuff, and
Oh, yeah.
then he was doing like the PCB. He was
Oh,
doing,
you know
like,
Reese.
Yeah, Reese.
Yeah, yeah.
He was my physics lab mate, but
Okay.
yeah, I
He's
was
great,
talking to him about it. He's like, yeah, I took this unicycle thing. I was so confused about it last year, and I was looking at some of your research. I was like, oh, never mind. Actually, kind of makes sense, but
Yeah,
Who's
it's
like-
great.
Where would I find your research?
I have a lab website. So if you Google my name and you find my website that's associated with the university, I think it has a link to my personal website. And the personal website has a little bit more detail about the research that I'm doing. But also there's been a couple articles about the project that have been like covered by the local news.
Oh, okay. I shouldn't.
Okay, I'm gonna stop recording on Zoom and I have to